Okay, welcome back, everyone. We'll get this session started with Micaela. There's the title of the talk. Oh.
Thank you. All right, so I'm one of those who's for whom this is the first RDKit UGM, hopefully not the last, but yeah, I think all you need to know, what you need to know about me is that I'm not, I have a little bit of a different profile from sort of with respect to probably most of you. So I'm a materials chemist. I am mostly a 3D computational person. So cheminformatics and all of this kind of drug discovery toolkits. And this is all very new for us. And we are trying to basically be the kind of people who like come here, steal a bunch of stuff, take it back to the people working on soft matter and look smart, basically. So if anything I will present or say sounds like, oh, you should definitely, why are you doing this? You should do that instead. Why don't you know about X tool? Like, please do let me know. This is absolutely why I'm here. So yeah. Right, so the thing is, what I find out is, as a new PI, I started my independent lab 3 years ago, and obviously desperate for money, right? And so what I found out is, as a person who works on polymers for optoelectronics, so OLEDs, solar cells, and all this kind of a niche applications of electronics, I found out that actually there is a lot of money in pharma. And so if only I could tap on that money, I would be super successful. So I started kind of increasing or sort of spreading myself outwards, looking at other problems with different polymers. And so I kind of landed on a collaboration with Johnson & Johnson on polymer formulation. I thought, well, I look at formulation of solar cells with different components. Surely I can look at drug formulation. How different would this be? And so that's kind of how we started looking into this kind of problems, where we want to optimize ways to deliver difficult drugs to using things like polymer nanoparticles or hydrogels. And we ask ourselves, how can we optimize a polymer to better deliver certain drugs for controlled release or things like that? So we are looking at different matching ideal sort of improving polymers so that it can match better with different APIs. Right, so, and coming from the world of polymer simulations and molecular dynamics specifically, the three bottlenecks are sort of how do you build your polymer structure, which parameters do you use, and how do we equilibrate that? So we are going to focus on the first problem, so polymer building, and the questions that I'm asked myself with this project, and I'm going to try and answer them partially, at least today, are, first of all, polymers are statistical objects. They are not just the same sequence that you just copy paste multiple times, you put in a box and you simulate. They have dispersity, they have different, they can be randomly sort of copolymers. They are statistical entities, and so we should probably ideally treat them as such and in simulations, and that's not routinely done. The other thing that we are interested in is we want to study polymer gels, networks, hyperbranched polymers, brush polymers, all these sort of like nice 3D complex objects, but we really like working with reaction smarts. And we want to see if we can apply sort of this kind of 2D polymer building tools to make this kind of complex morphologies. So we started by surveying the literature and what's available for building polymers. There's a bunch of stuff. But if you look at the capabilities of each tool, there are some limitations. And so if you look at, for instance, the kind of polymers that they support, right? So copolymers supported by basically all these tools. You can do branching, just kind of a matter of attaching stuff. They can do tacticity. So it's where you look at kind of the dispersity that you start to see, okay, not many tools actually have this kind of statistics built in. And also, how can we build our sort of input sort of from monomers? And so we realized that, okay, maybe we are going to develop our own tool that has this kind of dispersity built in and also can take reaction smarts as an input. And so this is why my very talented PhD student developed this tool called SwiftPol. So you can imagine who is her favorite pop star. I don't have any Taylor Swift puns because actually I don't think I can name you a single song from her. So I need to work on my sort of integrating this knowledge in the next presentation. But fundamentally, what we want to achieve with SwiftPol, and in general, basically for her PhD, is having a way to build fair polymer simulations. And right now, what we can do is we can build polymers in solution, melts, pre-equilibrated melts. We can do cross-linking, and we can add APIs or sort of whatever you want, small molecules, basically. Right, so let me walk you through some of the parameters that we want to take into account. So we work with a team of experimental polymer formulation scientists at Johnson & Johnson. And so they come to us and they have their polymers with specifications, right? So we want to be able to basically match, sort of build kind of a digital twin of that polymer using SwiftPol. So we have sort of the ratio of different copolymers. We have the blockiness, which is basically defined as sort of by this equation here. So how many sort of blocks of BB versus BA we have. We want to look at the degree of polymerization, of course, and which terminals we have. And then, of course, there's always some residual oligomer or residual monomer in this kind of products that you can buy. And so we want to be able to potentially match that as well. Right, so the way that this works is we take as input variables all these specifications that a polymer chemist would know because they are written in the batches that they work on. And we can use that information to build an ensemble of polymer chains that actually represent that sort of population. And then what else we do? We obviously go from the sort of 1D or 2D representation of that polymer chain to actually building the each 3D polymer chain, pack it in the box, and go on to sort of with your favorite engine to do MD simulations. So we use, so we started using PacMo. We realized that there's actually a much nicer tool called Polyply, which is essentially a random self-avoided random walk that enables you to sort of equilibrate your polymer so that you have a box with the kind of correct target density. And then using OpenFF interchange, we can export this into whichever MD format we need. And we are using OpenMM, but we could be using sort of clamps, GROMACS, you name it. Right, so just to give you an example, so we started working with PLGA, which is used in a lot of these different drugs. And so that was a kind of a natural initial target. Also, it's a copolymer. So we have defined our sort of monomer A and B. We can do our reaction smarts. And so you can see that it's relatively straightforward. So we have a bunch of notebooks in the repo that you can check out. So you can see how all of this can be customized to any different polymers. So yeah. Right, so looking at how fast is this, it's okay, it works well. So it's obviously, so we've done some stress tests looking at different sort of increase in chain length. So this is for a single chain, linear chain, no branching, no nothing. And it works pretty well. So we can build pretty much the systems that we want in the size that we want. So this is not going to be a bottleneck in our simulation pipeline, which is reassuring. So lots of love from us to the conformer generation. And yeah, so basically we looked at sort of comparing the conformer generator with sort of that we have within RDKit with the Omega tool from OpenEye. We are happy with the performance that we see sort of with either tool. We don't think that this is kind of a significant bottleneck. Again, the slow thing is always doing the MD simulation. So that's kind of what we need to keep in mind. So for instance, here we have an example where we take a commercially available polymer and all the specs, and we can see how we can closely match those with a kind of a replica that has roughly sort of a 40% of the actual molecular weight. So our polymer distribution is kind of shifted to smaller polymers just because we are in the world of all atom molecular dynamics. So it's expensive to actually match the molecular weight, but at least we can match the kind of overall distribution between residual oligomer, blockiness, and so on. So that's pretty good. And then now the problem is, what if we wanted to do more complex things? And I need to see if this video is going to play. So maybe I need to click this. Is that going to work? No. Okay, never mind. So the problem of building complex or looking at polymerization in MD simulations, there's different ways and they're all costly and they're very expensive. And a master student, sort of, it takes time to train people to perform this kind of simulation. So the alternatives that we have to build heavily cross-linked systems are basically, so if for the kind of maybe more older people in the crowd, if you remember ReactFF, basically reactive molecular dynamics simulation, this is the OG tool, but it's quite limited. It usually works well for systems where you are performing some kind of like graphitization. So you are at like really high temperature. There's very few parameters or very few atoms. It's not easy to use at all. And so that was just no, we're not going to do that. So next step is using this topology rebuilding tools that basically you are running a molecular dynamics simulation, and every now and again, when two monomers, they come in close contact in your box, you block the MD simulation, you perform kind of a random number generator extractor, which decides the reaction probability. And if your sort of random number says, yeah, okay, these two are going to react because they're close together, then you basically rebuild the topology where those two monomers are actually bonded together, and you restart your MD. You can imagine that this takes time, and then you have to be very good at defining exactly your constraints for how the topology is going to change, the initial, final steps. And so a master student is kind of, okay, they can teach themselves, but it takes time. Of course, the nuclear option, I mean, the ideal option would be, okay, we can use these NMPs, these machine learning potentials, they are great, but still quite slow and slower than an MD simulation, than a classical MD simulation. So maybe one day, but not right now. So what we decided is, okay, how about we try and do it with RDKit? See if basically the conformal generator basically gives up at some point. And the good news is that it kind of works. So we're able to cross-link a system like this one, which is this PEGDA diacrylate. You can perform cross-linking reactions, and you get this kind of really odd circle-looking ugly structures in 2D. But then I promise you that these export to 3D, they work. And yeah, so essentially we have a system to go from a one-dimensional polymer chain with a sort of a specified reaction smarts patterns for different cross-linking reactions. And then we can calculate some network properties, for instance, how many cross-links we have and sort of what our object looks like using network X. And we can export this to sort of an NMD simulation box pretty easily. And then, so the idea is that maybe you might not be able to sort of replicate exactly those MD polymerization protocols, but if you can seed your MD simulation with something that looks more like a smaller version of your network that you want to achieve, that's going to significantly speed up your workflow instead of starting from monomers or small oligomers. So yeah, so this is kind of a fresh implementation that we have in the in SwiftPol. In the latest version, we have this cross-linking tool. We have used this to sort of make rubber make different sort of pegged oligomers. Is this gonna play? Yes, okay. So again, the trick here is always that you can define your own reaction smarts, and so you can add as many crosslinks as you want. And yeah, it seems to work. We are still running sort of the benchmarking speed test, but we have simulations with sort of 50 or 60 different chains, individual polymer chains that are cross-linked together. So it seems pretty robust to do the kind of MD simulations that we like. Right, so growing pains, the moment I finished, I thought I was done with this slide, and then I had 5 more things that came out that I could have added. But fundamentally, this is still a little bit slow in the sense that we need to run the cross-linking ideally not on a laptop. So this is gonna run on a supercomputer. Ideally, we give it some kind of more computing resources than we would for a linear chain, but it's still not as low as running reactive ND. So I tell my students, just be patient, just leave it and just go do something else, read a paper, come back to it. And yeah, we're using halogen tags for reaction smarts. Maybe that's not the smartest idea. We could definitely improve our sort of treatment of sort of our literacy. And yeah, I've had some pretty good inspiration from just being here and listening to all of you. So thank you. And yeah, there's documentation. It's there, it works. We have a few examples. And so concluding my presentation. So we talked about polymer building. Should we account for dispersity in polymers? Like, does it actually make a difference? Well, stay tuned for the answer, because the reality is that if you are confined to all atom molecular dynamics, there's a limit to how big or how close to the sort of real life polymer your system is going to be. So the fundamental thing is we realized that nobody was actually looking for the effect of dispersity. And talking to experimental polymer chemists who do real sort of drug formulation, they know it's important, they know it matters. And so ideally, we should take this into account. Will it make a difference in our calculations of glass transition temperature, other properties? We don't know yet, so let's see. And then can we build 3D topologies with cross-linked, heavily cross-linked polymers using cheminformatics? Yes. It's definitely a better starting point than all the other alternatives available. And yeah, so our workflow now goes from sort of the sequence and polymer building to applying parameterization to those polymers up until pre-equilibrating melts. And we're using RDKit, we're using OpenFF toolkit, and we're using polyply and OpenMM. So yeah, that's our team. So I just want to thank Hannah, who is here pictured looking very happy because we were doing a site visit to Johnson & Johnson. She's going to spend a few months working there. So yeah. And yeah, the Johnson & Johnson team who has been involved in the project, and Jeff from OpenFF, and of course you for your attention.
We have time for a couple of questions if there are any.
Right. This is more of a comment, but if you ask people to raise their hand, whether they use Palatin or vanadium or anything, reactions to link things together quickly, probably be surprised how many people is there.
Okay, yes, the comment was, it's not that weird to use halogens or other weird chemistry to run reactions. Yeah, point taken.
I normally use plutonium. But
Okay.
anything else out there? So I have one, with the conformal generation, which conformal generator are you using? So which parameters are you using?
So that's the thing. I was like furiously typing this to my student. Like, we haven't looked at any we have to look into all these options because we've been just like
The default.
trusting it. Everything default. So yeah, there's a lot of room for improvement.
So I think for what you're doing, you probably want to use either KDG or just plain DG.
Okay.
Because you don't need the experimental torsions for what you're doing, because you're doing condensed phase and you're going to a force field anyway. So KDG or DG probably.
Right. Thank you so much.
And hopefully we then get more competitive with Omega, but Omega will always win for big systems.
Honestly, so there's some data that I'm not showing here because we were trying to redo a lot of the kind of the cross-linking stress test. And actually, you'll be surprised, but RDKit builds, Omega fails.
Oh,
So,
nice.
yeah.
Very good. We should stop there.